dear learners, I welcome you all to the first module, that is Fundamentals of Electricity of the SWAYAM MOOC on Electricity and Electrical Wiring. I am Dr. Smritimala Sharma, Assistant Professor in Physics, B. Borwa College, Guwahati. Module 1 has been divided into 3 units. In the previous session, you have learned about understanding electricity, where we have covered electrical energy, sources of electricity, atomic structure and principle of current flow. In the second unit of this module, we will discuss basic terms of electricity. Here, we will focus on electric circuit, electric field, electric potential, electrical resistance, Ohm's law, electrical power, resistivity and conductivity, electromotive forces. Electricity is a form of energy that results from the movement of charged particles such as electrons and protons. Electricity flows through a circuit, which is a closed loop of conductive material that allows electricity to flow. An electric circuit typically includes a power source, that is like a battery or the electrical grid. It also consists conductors like the wires or other material that allows electricity to flow. It consists of a load, that is, it is an electrical device that uses electricity such as a light bulb or a motor. It also consists a switch. Switch is a component that can open or close the circuit. For example, a simple flashlight circuit. When you turn on a flashlight, the switch closes the circuit, allowing the electricity from the battery to flow through the wires and light up the bulb. So, in a circuit, electrons move through the conductors when a potential difference is applied. This movement of electrons is the electric current.
Imagine a railway track with no beginning and end, that one we see in toys. Engine will keep on moving as far as the track is continuous. When one part of the track is removed, the engine will stop and cannot move ahead. Electric current is that train only. For current to move, it needs a path just like that train. It is called circuit. When path is complete, electric current moves instantly through it. When circuit is broken, it stops. Electric circuit has 3 parts: energy source, output device and wires. Energy source can be a battery or a generator. Output device is anything that will use current to do something useful, like turn on light, play music, move things like motor. The wire transmits electric current. Circuit usually contains a switch to turn current on and off. Turning off the switch creates a gap in the circuit that stops the flow of current. A circuit in which current is stopped is called open circuit. When switch is closed, the gap is removed from the circuit and current starts to flow again. This circuit is known as closed circuit.
Now let us see what is electric field. An electric field is a region of space around the electrically charged particles or objects within which other charged objects experience a force. This force can be either attractive or repulsive depending upon the types of charges involved. The direction of electric field is defined as the direction in which a positive test charge would move if placed in the field. The magnitude of the electric field at any point is the force per unit charge exerted on a small positive test charge placed on the point. Next, we are moving to electric field lines. Electric field lines are often represented by field lines which point away from the positive charges towards the negative charges. The electric field at a point in a space can be calculated using the formula given, that is E equal to F by Q, where E is the electric field, F is the force experienced by a test charge, and Q is the charge.
An electric field is a disturbance in space created by the presence of electric charge. The electric field at a particular point in space can be defined as the force per charge on a test charge at that point in space. For a single positive source charge as shown, the force and hence the electric field depend upon the position of the test charge. The field exists at every point in space regardless of whether there is a test charge there to sense it. An array of vectors can help visualize the field. These field vectors reflect the symmetry of the charge. In this case, they show the field is directed radially outward from the positive source charge. Electric field lines are another way of visualizing the electric field. Field lines are continuous lines that are tangent to the field at every point in space. That is, field lines are parallel to the electric field. The concentration of the field lines in a region of space is an indication of the strength of the field. The field lines will also reflect the symmetry of the field and of the distribution of charges that produce the field.
Let us move to the superposition principle of surges. If multiple surges are present, the total electric field at a point is the vector sum of the electric fields due to each surge. This principle is known as superposition principle. Dear learners, you have already learned about the electric potential in the previous lecture. Electric potential is a measure of the potential energy per unit surge in an electric field. Voltage is described as the pressure that pushes electric surges, that is the electrons, through a conductor. It is a driving force that causes electrons to move in a circuit. Let us now see the differences between electric potential and potential difference. Electric potential is the work done per unit surge to bring the surge from infinity to a point in an electric field, while potential difference is the difference between the potentials between 2 points in the electric field.
The rate of flow of charge in a conductor is called electric current. This is the electric current that lights the bulb. We know that charge is always present in the metallic wires. So why do we need to put batteries in the circuit for the bulb to glow? Why is it necessary to put the battery? In the process of the lighting of the bulb, another physical quantity works along with the electric current, which is called electric potential difference. What is this electric potential difference? Let us try to understand this with the help of this example. Have you ever poured water on horizontal leveled floors and on slopes? Does water flows the same way in both the cases? The answer is no. On the slopes, the water flows till it reaches the bottom, and on the horizontal floor, it will stop flowing after a while. In the case of slopes, no extra force is required, whereas despite applying force on the horizontal floor, water stops flowing as soon as the effect of that force tends to zero. So, what is the difference between these two circumstances? Yes, you get it right, height. Due to the difference in height, gravity and water molecules forced each other on the slopes, due to which the water flows till the lowest point possible. What will happen if in the place of a horizontal floor, a water pipe is taken? What do you think, that we get the water by this pipe simply when we open the tap? No, we can't get any water until there is a force from behind or there is a pressure. To create this pressure, the water pipe should be connected to a water tank. As there is plenty of water in the tank, there will be more pressure in the mouth of the pipe. And as soon as we open the tap when the pressure is low, the water starts flowing from the area having high pressure to the area having low pressure. Here too, like the slope, difference in pressure is obtained due to difference in height. So we can conclude that to let the water flow, we need a pressure difference. If the water pipe is replaced by a metallic wire and the water tank is replaced by a battery, then we get something like this. We know that the circuit must be closed for the current to flow. Let's attach the other terminal of the battery to the bulb. Electricity is also like this tank's example. To let the electric current flow, we need a difference in the circuit. Like there was a pressure difference in the analogy of water tank example. This difference in the circuit is known as potential difference. Just as the water flow from high pressure to low pressure area, similarly electric current also moves from high potential area to low potential area. The difference of voltage between one terminal of the battery and the other terminal is called potential difference.
The next topic is electrical resistance. Electrical resistance is the property of a material that opposes the flow of electric current. It is the friction that electrons encounter as they move through a conductor, causing some of the electrical energy to be converted into heat. The greater the resistance, the less current flows for a given voltage. Resistance is measured in ohms. There are some factors which affect resistance of a material, like the material. Different materials have different resistivities. For example, copper and silver have low resistances and they are good conductors, while rubber and wood have high resistances and they are insulators. Resistance depends upon the length. The longer the conductor, the more resistance it offers. This is because electrons have to travel a greater distance, encountering more obstacles. Resistance also depends upon cross-sectional area. A thicker conductor offers less resistance because there is a more room for the electrons to flow. Resistance depends upon temperature also. As temperature increases, resistance in most conductors increases. This is because atoms in the conductor vibrate more at higher temperature, making it harder for the electrons to pass through. Resistance in an electric circuit. In a circuit with multiple components, the total resistance determines how much current will flow for a given voltage. The relationship between voltage, current and resistance is given by Ohm's law. Georg Simon Ohm, a German physicist, discovered the connection between these three parameters. According to Ohm's law, the current flowing through a conductor between two locations is proportional to the voltage across the conductor. That is, if V is the voltage and I is current, then P is proportional to I and the proportionality constant is resistance, that is R. The Ohm's law tells us that for a given resistance, increasing the voltage will increase the current. For a given voltage, increasing the resistance will decrease the current.
It states that the current flowing through a conductor is directly proportional to the voltage applied across it. This condition is valid if the temperature and other physical conditions remain constant. The formula for the Ohm's law is V is equal to IR, where I is the current which is measured in amperes, V is the voltage or potential difference measured in volts, and R is the resistance measured in ohm. The technical details of Ohm's law are crucial for understanding how electricity works in circuit. For example, if you increase the voltage applied to the resistor while keeping its resistance constant, then the current flowing through it will increase proportionally. Similarly, if you decrease the resistance of the circuit while keeping its voltage constant, then more current will flow through it. One of the primary advantages of Ohm's law is its simplicity. Understanding Ohm's law can help engineers design circuits that operates efficiently and safely. By calculating the expected current flow through various components, engineer can select appropriate resistors and other components to prevent overheating or damage. Without an understanding of Ohm's law, electrical system can be dangerous and unreliable. Ohm's law formula and technical details are essential concepts for anyone working with electricity or electronics. Understanding this law allows engineers to design safe and efficient circuits that meets their intended specification. The simplicity of the law and versatility make it an essential tool for designing effective electrical system.
Next, we are moving to the topic of electrical power. The power of an electrical circuit refers to the rate at which electrical energy is consumed or converted into another form of energy, such as heat, light, or mechanical energy. It is measured in watts and it represents the amount of energy used or produced per unit of time. The formula for electrical power is given below. Here you can see the power in an electrical circuit is calculated using the formula P equal to V into I, where P is the power in watts, V is the potential difference across the component in volts, and I is the current flowing through the components. There are different types of power in an electrical circuit. We may have active power or the real power. This is the actual power that performs useful work in the circuit, like lighting a bulb, heating a coil, or powering a motor. It is given by the formula P equal to V into I, where the voltage and current are in phase in case of an ideal resistive circuit. In case of reactive power, in circuits with inductance and capacitance, some of the power is stored temporarily in the magnetic or electric fields and then returned to the source without being consumed as useful energy. Thus, reactive power doesn't perform any useful work but is essential for the functioning of inductive and capacitive loads like motors and transformers. In case of apparent power, it is the total power supplied to the circuit, which includes both active power and reactive power. We are moving to the power consumptions in household appliances. In case of incandescent light bulb, it may use 60 watts of electrical power to generate light and heat. In case of electrical heater, it can use 1500 watts or more power, converting electrical energy into heat. In case of the computers and electronic devices, they may use powers of 200 to 500 watts depending on its different types of components and activity levels. In our laptops, they may use 30 to 60 watts of power. There may be power losses in case of the circuits. The reactive losses occur due to the resistance in the wires and components of the circuit, and these losses generate heat. To reduce these losses, wires with lower resistance may be used. Let us go for an example. Let us calculate the power consumed by a resistor in a circuit. Suppose you are given a voltage of 12 volt and current 3 ampere. Using the formula for power, we can get the power to be 36 watt, as you can see in the slide. Now let us go through a quiz. Hope you have enjoyed this quiz. Next we are moving to resistivity and conductivity. Resistivity and conductivity are two important properties of materials that describe how easily they allow the flow of electric current. Resistivity is a material property that quantifies how strongly a material resists the flow of electric current. It depends on the nature of the material. It is independent of its shape or size. The higher the resistivity, the more the material resists the current. So here you can see the formula for resistivity. It depends upon resistance, it depends upon length of the material, it also depends upon the area of cross section of the material. The SI unit of resistivity is ohm meter. Conductivity is the reciprocal of resistivity and it measures how well a material allows the flow of electric current. Materials with high conductivity are good conductors, while materials with low conductivity are poor conductors, or we can say insulators. The SI unit for conductivity is Siemens per meter. Dear learners, now we are moving to the electromotive force. Electromotive force refers to the energy provided per unit charge by a source, which drives the flow of electric current in an electrical circuit. EMF is not a force in the traditional sense, but rather a potential difference or voltage that causes current to flow. It is generated by sources that convert other forms of energy such as mechanical energy, chemical energy or thermal energy into electrical energy. So some examples of EMF are the batteries, the generators, solar cells, the thermoelectric generators, etc. Dear learners, let us now move to a very important topic in case of electrical circuits and wiring, that is short circuit. A short circuit is an electrical fault that occurs when there is an unintended connection between 2 points in an electrical circuit, typically resulting in a path of very low resistance. This allows a large amount of current to flow through the circuit, which can cause overheating, damage to the components, and even fires if not quickly addressed. In a normal circuit, Electrical current flows through components like resistors, bulbs, or appliances which offer a certain amount of resistance. However, a short circuit occurs when the current bypasses these components and takes a shortcut flowing directly through a conductor, typically when a wire touches another wire or a grounded surface, a component fails inside the circuit causing its electrical path to short circuit, or a connection becomes faulty due to improper wiring, wear or damage. Now let us move to the characteristic of a short circuit. Low resistance path. When a short circuit occurs, the resistance between the 2 points is very low, almost zero, so the current increases dramatically. There may be excessive current flow. Since the current has little resistance, it increases far beyond the normal operating levels. This can be many times higher than the current the circuit was designed to handle. There may be generation of heat. The large current flowing through a low resistance path can generate a lot of heat which can melt wires, damage components, or even start a fire. There may be tripped circuit breaker or blown fuse. In most circuits, short circuits are designed to trigger safety mechanisms like circuit breakers or fuses. These are the devices that interrupt the flow of current to prevent further damages. Overheating, damage of components, power losses, and fire hazard may be some effects of short circuits. To prevent and handle short circuit, there must be uses of circuit breakers and fuses. Proper insulation should be there, regular maintenance should be there, and ground fault protection should be there. Next, we are moving to circuit breaker. A circuit breaker is an essential electrical safety device used to prevent damage to an electrical circuit due to excess current flow. It automatically interrupts the flow of electricity in the event of an overload, short circuit, or fault, thereby protecting the wiring, appliances, and other electrical components from potential damage or fire hazards. A circuit breaker continuously monitors the flow of electricity through a circuit. When the current exceeds a set threshold, either due to an overload or a short circuit, where current flows along an unintended path, the circuit breaker detects the issue. The circuit breaker trips to stop the flow of current, disconnecting the electrical circuit and preventing further damages or danger. Once the issue is resolved, the circuit breaker can be manually reset to restore power to the circuit. There may be different types of circuit breakers like thermal circuit breaker, which uses heat to detect the overloads. When current flows exceeds a certain level, it causes a metal strip to bend or open the circuit. In case of magnetic circuit breaker, it uses a magnetic field to detect the short circuits. The increased current creates a magnetic force that strips the breaker. There may be combination of circuit breaker in which a combination of both thermal and magnetic features providing protection against both overloads and circuits are used. Circuit breakers are used in residence, in commercial places and industrial places.
A circuit breaker is a safety device that interrupts the flow of electricity in an electrical circuit. The purpose of a circuit breaker is to prevent damage from overload or short circuit. There are two main types of circuit breakers. 1. Thermal magnetic circuit breakers. 2. Solid-state circuit breakers. Thermal magnetic circuit breakers use a combination of heat and magnetic force to trip the breaker, while solid-state circuit breakers use semiconductor devices to detect an overload or short circuit, and then interrupt the flow of electricity. Lastly, circuit breakers are typically installed in household and commercial buildings, as well as in industrial and utility applications. Overcurrent. Overcurrent is a condition of an electrical circuit when it exceeds the maximum current allowed. As a result, too much current is flowing through the circuit. This can lead to fires, damage to the conductor insulation, and equipment damage. Overcurrent can be caused by a number of things, such as short circuit, overload, ground fault or arc. Due to the potential damage caused by an overcurrent, it's important to shut off the power to the affected circuit as soon as possible. Overload. An overload happens when equipment is operating in excess of its normal full load rating. When this is sustained over a long period of time, it causes overheating and damage. An overload can be caused by a number of things, for example an overloaded circuit, or faulty appliances. Overloads can cause damage to electrical components and pose a fire hazard, so it's important to shut off the power to the affected circuit as soon as possible. Short circuit. A short circuit is caused when an overcurrent extremely exceeds the recommended full load current of the circuit. As the name suggests, a short circuit is when the current travels along an unintended path, taking a shortcut around the load and then back to the power source. As a result, this leads to an excessive current flowing through the circuit. A short circuit can be caused by a loose wire, damaged appliances, or an overloaded circuit. Why do circuit breakers commonly trip? There are a few reasons why circuit breakers commonly trip, such as 1. Overloaded circuits. Too many devices drawing power from the same circuit can cause it to overload and trip. 2. Short circuits. A direct connection between the hot and neutral wires of an electrical circuit can cause it to overheat and trip. 3. Ground faults. When the hot wire of an electrical circuit comes into contact with the ground, it can cause the circuit to trip. 4. Appliance failures. A faulty appliance can cause a circuit to trip. If your circuit breaker trips frequently, it's important to have an electrician check your wiring to ensure everything is up to code, and to identify any potential problems. How do circuit breakers work? Circuit breakers work by detecting when an electrical circuit is overloaded or has a short circuit. When this occurs, the circuit breaker trips and interrupts the flow of electricity. This prevents damage to the electrical circuit by preventing further current from flowing. What are the benefits of using a circuit breaker? Circuit breakers offer a number of benefits over other types of electrical safety devices, such as fuses. Circuit breakers can be reset after they trip, while fuses must be replaced. Furthermore, circuit breakers also provide protection against both overloads and short circuits, while fuses only provide protection against overloads. Additionally, circuit breakers can be used in a variety of applications, such as household, commercial, industrial, and utility applications.
Now, dear learners, let us go through a small quiz on the topic that we have discussed. Dear learners, we have come to the end of this session. So in this session we have learned about electric field, electric potential, Ohm's law, electrical power, resistivity and conductivity, electromotive force, short circuit and circuit breaker. Hope you have enjoyed this session.